Alright, welcome to 3030, and today we're going to discuss a new lecture, number 18, and this is about the DRAM memory, and DRAM is short for the dynamic random access memory. And we have discussed that the different memory technologies in the memory hierarchy, and we have seen that the SRAM is used for the cache on the processor, and SRAM is the closest to the processor and is built on the same chip as your processor. But the DRAM is the next level. It's on the separate chip and is off chip, and this is used for the main memory. So let's get started on the DRAM. And this is a reference chapter in the textbook, and also the Professor Asif Khan's recorded video. Alright, so let's look at the DRAM. I assume that many of you have seen this kind of DRAM chip before. So if you open the desktop, you can find this kind of circuit board, this green board, with the DRAM chips on that. So here, these black chips are the DRAM chips. There are 4 chips on this circuit board. And then this DRAM circuit board is going to be inserted into the motherboard of your computer, and then the motherboard will have the data bus communicate with the processor. So your data is transferred between the data bus through the data bus from the DRAM to the processor. And typically here you will have like 64 bits I/O. So every cycle you are going to transfer 64 bits, or sometimes you can have 128 bits I/O width. So depending on the design, you may have different number of bits to be transferred at the same time, but the bits are transferred through the data bus. So it's off chip. It's not on the same chip as your processor. So here we can look at some specs of your computer system. And here are just some examples from the MacBook. And if you look at the specs here, it will list the processor it used. And for example, here we have the Intel i5 or i7 processor with the clock frequency up to 3.2 gigahertz. And then we have this 8 gigabyte memory. It didn't say what kind of memory it is, but you will realize that this actually refers to DRAM, dynamic random access memory. Or similarly, this 16 gigabytes for this higher end version. And then you will see another memory, like 128 gigabyte to 56 gigabytes, or this 512 gigabytes. So this is the SSD, and we are going to discuss that later. This is based on the flash memory technology. So you will see that the many different technologies used in the memory hierarchy, as we discussed. There's a trade-off between the speed and the capacity. And you know the SRAM is the fastest and is embedded on the processor. So if you want to further look at the specs of the SRAM, like the L1, L2, L3 level, what is the capacity? You need to go to the Intel's model number, like i5. There must be an extension i5, for example, 3030. Then you need to go to that model number and look at the specs. So what you can do here from your computer is to look at the task manager. And if you do that, and then if you look at the performance, you will find out the CPU. For example, this is my laptop. So you see this is based on Intel i7, and the extension is 8650U. This is the model number. And you can see that here we have 3 levels of cache made of SRAM. And Level 1 is 256 kilobytes, level 2 is 1 megabyte, level 3 is 8 megabytes. So this is consistent with what we discussed in the last lecture. And then here you will also find the memory. So this memory is the DRAM. And in my case, my memory capacity is 16 gigabytes for the DRAM. So this is based on my laptop. You can look at your laptop if you are using Windows. All right, any questions so far? So if you have questions, you can use the chat function, or you can unmute and ask the question. Okay, so let's dive into the DRAM here. DRAM is short for dynamic random access memory. Let's look at the first term, dynamic. This means periodic refresh is needed, and we're going to discuss what is this periodic refresh later. This is different from the SRAM. So SRAM, no periodic refresh. And again, this is random access, so it's a run. That means each bit can be accessed, read or write, independently. That means no matter which location of this bit in your memory array, you can individually read it or write it. And again, this is volatile memory. This is similar as SRAM. If the power supply is removed, you will lose the memory state, or your data will be gone. So those are the key features for the DRAM. The only difference with SRAM is this dynamic feature. We need periodic refresh, and we'll discuss what does that mean in the later slides. All right, let's look at the DRAM cell structure. So this is to store 1 bit information, and we need this 1 DRAM cell. And it's very simple from the circuit schematic. You can see here, we have 1 transistor, 1 capacitor, so we call it 1T1C cell. This is to store 1 bit information. And we have this NMOS transistor. This is NMOS. And the NMOS gate is controlled by the VLAN. And the NMOS, let's say source or drain, one side is attached to the bit line, the other side is attached to this capacitor, and we call this storage capacitor, and it has a capacitance CS. And this node is important. This is called the storage node, SN. So the information is stored on the charge in this node, because this capacitor can hold some charge. If you store 1, that means this SN node will carry some charge, and this SN node will be VDD. So if you store 1, then this will be VDD. If you store 0, then this will be 0 or ground. So you know this is based on the charge on the capacitor CS. If you have some charge, you can be VDD voltage, and then you store 1. If you don't have charge, then this is 0 voltage, and you store 0. So this is a basic structure of the 1T1C cell. It looks simple. And let's say, how do we do the write or the read operation on this cell? If you want to write the data in, if you want to write, for example, write 1. So what you need to do is to prepare this 1 from the bit line. And then you turn on the VLAN. You need to turn on the VLAN. So VLAN will be 1. So you need to turn on the VLAN. After you turn on the VLAN, this is control the gate of the NMOS. You know the NMOS will be turned on, so the current will flow depending on the voltage of those two sides. So if you initially store 0, and now you want to write 1, so you have 1 here. You know the current will be this way, and then this VDD is going to charge this capacitor from 0 to VDD. So you're going to write this 1 into this cell. On the other side, if you want to write 0 and initially it stores 1, then the current will flow the other way. So this 1 will be discharged to be 0, and eventually this will become 0. So you write 0 into the storage node. So depending on the data you want to write, so you need to prepare the voltage on the bit line. If you want to write 1, then the voltage will be VDD. You prepare that, and then you turn on the VLAN. Or if you want to write 0, the BL need to be prepared to be 0, and then you turn on the VLAN. So the corresponding data will be written into the storage node. So this is for write operation. And then let's discuss the read operation. How do you want to read the data out? If you want to read the data, okay, one thing you need to do is to pre-charge the bit line to be half VDD now. This is unlike write. The write operation, we say that you need to prepare 1 or prepare 0 as a bit line. But the read operation, because you want to read the data out, before you read, you don't know what is the data inside the cell. So you assume it's in the middle. Okay, that means you apply half VDD to the bit line. You prepare the bit line to be half VDD. So let's say if you read 1, what will happen? So the BL you pre-charge to be half VDD. Okay. So let's say if you read 1, this is pre-charge. So this is half VDD now. And if you read 1 here, this node is VDD. Now you turn on the VLAN, so the current will flow. And you see that still the current will flow to the right, because in this case, still the left side is the drain of the transistor because it has higher potential. And then the right side is the source of the transistor because it's half VDD. And you know this transistor source and the drain is arbitrary, depending on which side has higher potential. The higher potential is the drain for the NMOS. So if you source 1, you see that the current will flow from the storage node to the bit line, like this. So this is like a charging current to the bit line. And we know that the bit line will have the parasitic capacitance due to the wire. This is the same as the SRAM case. You have long wire and multiple columns in the memory array. Between columns, you have the isolation. So the metal wire with isolation will form the capacitor in between. So you have the bit line capacitance, CBL. In this case, you are going to have current flowing from the storage node to the bit line. That means you're going to charge the bit line up. So that means the bit line voltage will increase from the half VDD, let's say by some voltage delta V. So here then this voltage will change from half VDD to half VDD plus delta V. Oops. So this is after you turn on the word line. How about you read 0? So that is this case, okay? So you turn on the word line, now the current will flow to the left because the right will be half VDD. The left is 0, so current still flows to the left. And then it's like you are going to have current discharge this bit line capacitance. So this voltage on the bit line will decrease by some voltage, and we say it will be decreased by the delta V. So this is your read 1, and this is your read 0. You see the difference between those two data patterns. And then the sense amplifier. So here you are going to connect this to an amplifier to amplify this small difference, delta V and positive delta V and negative delta V. So the output will tell you this data stores 1 or 0. If it's plus delta V, then you read out 1. If it's minus delta V, you read out 0. So any questions here? All right, so let me stop.